anytime an object moves inside a rotating reference frame, a non-inertial reference frame, that object will experience a pseudoforce known as the Coriolis force. Now, this Coriolis force is basically a result of an acceleration that is called the Coriolis acceleration, and the equation that gives us the quantity of this acceleration when we're inside the non-inertial frame is given by this formula. So 2 multiplied by omega multiplied by v, where v is the velocity of our object on that rotating frame that is perpendicular with the axis of rotation, and omega is our constant angular speed of that rotating frame. So in this lecture, we're actually going to derive this equation. But first, let's begin by setting up the following 2 important diagrams that we're going to use to essentially derive this equation. So let's begin with diagram 1. So let's suppose we have a rotating reference frame, a non-inertial reference frame that has an axis of rotation as shown by the following dot, which is basically coming out of the board. And this entire frame is rotating in a counterclockwise direction with a constant angular speed given by omega. Now, on that rotating frame, we have 2 people. So 2 people at rest. Person 1 is found at position 1 and person 2 is found at position 2. Now, at some initial time of t equals 0 seconds, person 1 at position 1 takes a ball and rolls the ball and releases it with a velocity given by v that points in the same direction where person 2 is standing at position 2, and the velocity points in a positive direction along the x-axis. Now, let's suppose we are inside an inertial frame, so we're a person standing on the outside of this rotating frame, and we're basically observing this rotating platform. Now, to this observer, this person standing at position 1 will have a certain tangential velocity that will point tangent to the rotation of that platform. So that basically means when the person releases that ball, not only will the ball travel with the velocity v in the positive x-axis, but it will also travel with a certain tangential velocity in the positive y-axis, let's say given by v1. So because the person and the ball are initially at the same exact position, they have the same exact tangential velocity that points in the positive direction along the y-axis given by v1. So basically, as a result of our velocity along the x and y-axis, these 2 velocities will add up to basically create a vector, velocity vector, that points at an angle with respect to the x-axis. And so that means this observer will see our ball travel along the following dashed line as shown by this line. So, once again, imagine that 2 people are found on a rotating platform, one at point 1 and a second person at point 2. The person at point 1 at some initial time t equals 0 seconds rolls a ball with a velocity v to person at position 2. But because the platform is rotating according to this person, it has another velocity that basically points upward along the y-axis that is called the tangential velocity, and these 2 velocities will add up and cause the ball to move along the following dashed line. Now, let's move on to the second diagram. So we still have our observer, and we're observing from the non-inertial, or we're observing from the inertial reference frame. So our platform is still rotating with a constant angular speed given by omega. So when our frame rotates, when this platform rotates, not only will the ball rotate, but the people at position 1 and position 2 will also rotate. So let's recall for a second the equation that gives us the velocity of an object that is found on top of a rotating platform. So in our discussion on rotating platforms, we said that the velocity is equal to r multiplied by omega, where r is the distance from that person or the object to the axis of rotation. So basically, the farther away that object or person is away from the axis of rotation, the greater the r distance is, the greater the velocity of that object or person. So the velocity that points upward along the y-axis of person 1 is v1, and the velocity that points upward along the y-axis of the ball as it travels along this dashed line is also v1. However, the velocity of person 2, let's suppose, is v2, and it's greater than the velocity v1. Now, why is that important? Well, basically, this means that when the ball reaches the outer edge, let's suppose this point here, it will reach a point which person 2 has already passed. So basically, because the velocity of person 2 is greater than the velocity v1, this person has already passed this point when the ball reaches that point. So let's suppose the distance that the ball and person 1 travels along the y-axis is given by d1. The distance person 2 has traveled along the y-axis as our platform rotates is given by d2. Now, let's suppose the radius of position 1 is r1 and the radius of position 2 is given by r2. So let's begin our derivation by using this equation. So v is equal to r multiplied by omega. And let's actually find the velocity v1 and v2. So v1 is equal to r1 multiplied by omega, and this gives us the velocity of person 1 as well as the velocity of the ball as it travels in the positive direction along the y-axis. Let's call this equation 1. Equation 2 gives us the velocity of person 2, so v2 is equal to r2 multiplied by omega. Now, notice that the ball moves radially outward a distance given by r2 minus r1. So the question that we're asking here is, what is the distance along the horizontal axis that the ball actually travels? So we're assuming the ball is at this position. So that means the ball traveled the distance from 1 to 2, from point 1 to point 2. So that means to find this distance, we simply take this r2 and subtract r1, and we get this distance between these 2 points. So basically, ball moves radially outward a distance r2 minus r1. Now, the velocity of the ball along this horizontal axis is given by v. That's the same velocity that person 1 gave to that ball given by v. So if the time that has elapsed during this trip is given by t, then we can find equation 3. So r2 minus r1, this distance is equal to the velocity of that object, the ball, along the horizontal axis v multiplied by t. So let's call this equation 3. Now let's move on. So during this same time interval of t seconds, the ball moves an upward distance of d1, and d1 is equal to the velocity along that same direction v1 multiplied by t. So for equation 4 is d1 is equal to v1 multiplied by t. What about person 2? So person 2 began at position 2 and eventually reached this position here. Now, this distance we said is given by d2. And to find the distance d2, we multiply the velocity of that person, v2, multiplied by t. So that's equation 5. d2 is equal to v2 multiplied by t. So finally, let's move on to the final step, or the final several steps. So we see that the ball passes behind person 2 a distance of, so now we want to find what this distance d is. To find this distance, we take this distance d2 and subtract distance d1. That will give us this remaining distance. So d is equal to d2 minus d1. Now we know from equation 4 and equation 5, d2 is equal to v2 multiplied by t, and d1 is equal to v1 multiplied by t. So d is equal to v2 multiplied by t minus v1 multiplied by t. Now let's go back to equation 1 and equation 2. So equation 2 gives us v2 is equal to r2 multiplied by omega, and v1 is equal to r1 multiplied by omega. So we replace these two quantities with these equations as shown. So notice each term has an omega and a t. So we can take those terms out and we get this equation. So d is equal to r2 minus r1 multiplied by omega times t. Now let's go back to equation 3. Equation 3 tells us that r2 minus r1, which appears in this term, is equal to v multiplied by t. So we can replace this with v multiplied by t. So d is equal to v multiplied by t multiplied by omega times t. The t's appear twice, we combine them. So d is equal to v multiplied by omega multiplied by t squared, where d is our displacement as shown in the following diagram. Now, notice the form of this equation has the same exact form as displacement of an object under constant acceleration. So d is equal to 1/2 a times t squared. So we set this equation equal to this equation and we get this result. Notice we can cancel out the t squares and we can solve for the a. And the a is equal to 2 multiplied by omega multiplied by v, which is the same exact equation as the equation for the Coriolis acceleration, which we mentioned previously. So 2 multiplied by omega multiplied by v. So basically, if we are found inside the reference frame of this rotating platform, according to the people on this platform, where exactly will that ball end up? Well, according to these people, the ball will actually end up somewhere in this location. And this distance is basically the same distance d that we derived for the inertial reference frame. So this distance d is the same as this distance d.